in past is on balancing redox reactions. So when you have a redox reaction, that stands for reduction or oxidation, and it's a transfer of electrons. One element is losing electrons, another one is gaining the electrons. And we have to account for those electrons lost or gained. This is a different way to balance reactions. Some very simple redox reactions can be balanced by just looking at them, which is how we balance most other reactions. But some reactions, you must go through a special process, and this is called the half-cell method. So I have your notes page here. You can print that out. I have it attached to the classroom. It talks about how to do the half-cell method. The first thing you're going to want to do is assign your oxidation numbers to each element and ion. So I have a little example here, and we have some iron 3 oxide that we need to figure out the charge for. Oxygen is going to be 2-, and when it's ionic like this, it's pretty easy. You can just uncrisscross, and iron is 3+. Here I have carbon and oxygen. They have to add up to equal 0 because there is no charge on carbon monoxide. Oxygen is almost always 2-, and if they have to add up to equal 0, that means carbon is 2+. On the other side, I just have iron by itself. That means it has an oxidation number of 0. It's all metallically bonded to other iron atoms. And then I have carbon dioxide. They have to add up to equal 0 because there's no charge on carbon dioxide. Each oxygen is 2-, and I have 2 of them. So that's a total charge of 4-. So carbon must be 4+ in order to create a 0 charged element. Now that I've done that, I can see which elements are being oxidized and which elements are being reduced. I can see that I have iron here going from 3+ to 0. The oxidation number is going down, so that means that iron is being reduced. And I can see the only other thing that's changing is carbon. Carbon goes from 2+ to 4+, so that oxidation number is increasing. So that means carbon is being oxidized. Alright, so a lot of times that's a part A or B to this type of question of which elements are being reduced and which are being oxidized. Alright, we're going to write the ionic equation, splitting ionic compounds. At this point, I think we're at a point where we need to go ahead and just go to writing the half reaction for oxidation. So we know that carbon's being oxidized. So I am going to just write down the things involving carbon because that was the one that was oxidized. I'll still keep the arrow in between those two. So my half reaction is going to look like this. So just the two things that involve carbon. If there were more things that involve carbon, I would have to put them in there as well. Then, this A through C here. I call this mode. And it's just kind of a shortcut for all the things that we're going to be doing. I have something better for basic solutions. And this is all in acidic solution. That's how it's going to start. You have to balance the mass, and that's anything that's not oxygen or hydrogen. Then you're going to, in acidic solution, balance your oxygens by adding water, and your hydrogens by adding H+. Since it's in acidic solution, we can expect some of that floating around. And then E stands for the electrons, and goes back just a second. Alright, so first thing we need to do is balance mass, and by mass I mean anything that's not carbon or hydrogen. So we can see here I've got 1 carbon and 1 carbon, so we're done with mass. Now it's oxygens. We balance oxygens by adding H2O. I have 2 oxygens on the product side, and I have only 1 oxygen here on the reactant side. So I need another oxygen, so I'm going to add water. That's how we balance our oxygens. Now I have to balance my hydrogens. That's the next step in mode heat. Now we balance our hydrogens by adding H+ in acidic solution. So on this side here, I have 2 hydrogens, and so I need 2 hydrogens over here on the reactant side. So I'm going to add 2 H pluses to balance my hydrogens. So now I've done mass, I've done oxygen, and I've done hydrogen. Now I need to balance electrons. So the charge on both sides has to be equal to each other. They don't always have to be equal to 0, but they have to be equal to each other. So I have 2 neutral compounds here on this side for a total charge of 0. On this side, I have 1 neutral compound, which is carbon dioxide, and I have 2 positives in the form of that 2H+. So I have a total charge of 2 on this side. Remember that electrons are negative, so I'm going to add electrons to this side, and I need to add 2 of them so that my total charge ends up being 0, just like the other side. Now that reaction is done. I'm going to erase this charge here. Now we have to do the other half reaction. So let's do the part where it is being reduced. So here we are in step 5. Alright, so iron is the one being reduced, so I'm going to write down the 2 substances, and if there were more, I would write more of them that involve iron. So iron is Fe2O3, oxide, and then hydrogen. Alright, we're going to go through that same process of Mohi. So mass, well, I've got 2 irons on the reactant side and 1 iron on the product side, so I need to put a 2 here. Now I need to balance my oxygens. I have 3 oxygens on my reactant side, so I need 3 oxygens on my product side. Then I need to balance my hydrogens. I'm going to balance hydrogens by adding H+. On my product side, I have 6 hydrogens, so I need to add 6 H pluses on this side. And now I have to balance my charge with electrons. So on this side, I have 6 positive things and a neutral compound, so I have a charge of 6 on this side. And on the other side, I have 2 neutral things, so this charge is 0. That means I need to add my electrons to this side, so 6E negative on that side, to give me a total charge of 0, which matches the other side. Now, what this is saying is this reaction, and when you notice, when you do a properly balanced redox reaction, this method, your electrons should end up on opposite sides, one on the left and one on the right. Now, these electrons you have never seen in a chemical reaction, and you won't, because the next step is to try and get rid of them. So I'm down here at step number 6, and what we need to do is understand that in this first reaction, it is releasing 2 electrons. In the second reaction, this iron is gaining 6 electrons. Well, that's 4 more than what was released in the first reaction. And that can't be. We can't just produce electrons just because we want to. So what we have to do is we have to adjust the coefficients in front of the electrons. Number lost in oxidation equals the number gained in reduction. The way you do that is you have to multiply one reaction or sometimes both reactions by a number, and I mean the whole thing. In this case, I'm going to multiply this reaction by 3 so that my electrons, I can have the same number on each reaction. So if I multiply all the coefficients by 3, you get 3, 3, this is going to end up being 6, and this is also going to end up being 6. Now my electrons are the same, being lost and gained. So I'm now at step number 7, where I have to combine the half reactions. I can cancel out anything common to both sides. So we're going to add this together. Kind of like what we did with Hess's law or something like that. So 6 electrons, 6 electrons. It doesn't matter which equation they're in as long as they're on opposite sides of the arrow. So it's helpful to line up your arrows between this. Other things that cancel. My 6H plus and my 6H plus on this side. Sometimes you'll be left over with your answer with H pluses, and that is okay. It's just in this case we didn't. Same thing with waters. I have 3 waters, 3 waters. They completely cancel out. Sometimes you'll have leftover water or 2 on one side or the other. Now, there's nothing left to cancel out, so I'm just going to rewrite it. I like to write it in the same order that it was in originally given to me. Do not leave out coefficients, because that's kind of the whole point.